Hello everyone, I am Alak and today I will be presenting our work improving image synthesis with diffusion-negative sampling. Although significant progress has been made in the field of text-to-image generation, current T2I models have several limitations in terms of adhering to the prompt specifically. In terms of enforcing multiple objects and their attributes, it suffers from attribute leakage, swapped attributes, or missing them completely. It is also notoriously hard to create human hands and fingers, as diffusion creates merged, extra hands, missing limbs, etc. To combat lack of prompt adherence, the stable diffusion community came up with the negative prompting concept, where negative prompts define what the image is not about and clarifies users' intention. These negative prompts work exceptionally well when attempting to remove specific or subtle things. While negative prompts do work well, most of the time it is unclear what these negatives are. Like there is no clear negative for a prompt, a cat and a dog. It took multiple attempts to get a negative prompt which actually works, and the negatives are also different for different seeds, as can be seen in these images. We hypothesize that this is due to diffusion's concept of negative not aligning with our semantic negatives. In this work, that's why we directly want to learn the negatives from the diffusion models and use them to come up with a final image. To understand this, we will first look at some preliminaries about diffusion, negative prompting, and its energy-based modeling. The implementation of negative prompting is quite simple. It is similar to the classifier-free guidance, where the final epsilon phi is replaced with the epsilon n, and n is the negative prompt. Using energy-based interpretation, the negative prompting can be modeled as sampling from probability np, which is proportional to probability of zt times gamma np power s, where gamma np is probability of zt given p divided by probability of zt given n. And hence, the negative prompting increases the probability of sampling zt of a large odds ratio, which is defined as the ratio of probability of p given zt upon n given zt. From this, we can conclude that through Bayesian decision rule, if the odds ratio is greater or equal to 1, then the prompt P is chosen, otherwise the prompt N is chosen. And so we need to learn a prompt N star, which increases the odds ratio for a given prompt P. We will use this fact to find out the optimal negative, and we will perform our proposed method, diffusion negative prompting. Our overall pipeline consists of 3 steps. Given a prompt V, we probe the diffusion model with our diffusion negative sampling, which we call DNS, to create a diffusion negative image. We then extract the negative prompt N star from this diffusion negative image, and finally use this negative prompt N star along with the original positive prompt P to get the final image. The crucial part of the overall pipeline is the DNS algorithm itself. To come up with this DNS sampling, we first define the optimization problem which maximizes the odds ratio, which will make the diffusion model adhere to prompt more. And so the optimization problem is defined as the argmax of derivative of log likelihood of the odds ratio. Solving the optimization via Lagrange, we get that the probability of zt given n star is inversely proportional to probability of zt given p. However, this is an improper distribution and a negative condition must always be specified in a context. And so we use empty prompt as the context and come up with the final solution in terms of gamma diffusion negative as probability of zt divided by probability of zt given p. This is equal to doing inference with epsilon is equal to epsilon phi minus s times epsilon p minus epsilon phi. Comparing this with the classifier free guidance equation, it is exactly the same, but now with a negative guidance. Now let's take a look at some of the qualitative results. Here we highlight qualitative results for various prompts. As you can see, it increases the image quality as well as prompt adherence. One thing to note here is that the negative images are not at all related to the prompt, which emphasizes our hypothesis of the negative space of diffusion not being equal to the semantic space. In conclusion, we hypothesize that the semantic gap between diffusion models and humans is responsible for the poor performance of the negative prompting. Diffusion negative images provide insight into this diffusion space to the user and gives them the true negation for a given prompt. This takes the guesswork out of the negative prompt generation and in turn creates a more robust system for the user. Thank you for listening. Please feel free to visit our project page for more information.